We consider the problem here of solving the second order linear differential equation. Again, we'll go through our quick checklist. Linear in y, yes. Constant coefficients. Yes, we have a 1 in front of both of these and a 0 implicitly in front of y prime. And homogeneous. Also check, the right-hand side in this standard form is in fact 0. So we do our usual thing. We're going to assume that y is equal to e to some power times x, e to the rx, and when we do that, that jumps us straight to the characteristic equation. In this case, it's very simple. We have a second derivative here, so we have an r squared. There's no derivative here, but there's a 1 multiplier, so we end up simply with r squared plus 1 equals 0. And this doesn't have really nice real solutions, but we can set r squared equal to -1, and then technically r would equal plus the root of -1 and negative the root of -1. Now for some of you, we're about to embark on a journey that might make you a little uncomfortable, because we are going to make strong use of this square root of -1 idea. Some of you will have seen this before. There's a notation for this that is the square root of -1 is sometimes called I. For now, what we can simply do is write these out as if they were the regular kinds of solution. y1 would be our first r value, square root of -1, times x. Our second solution would be the second root. It's a different non-existent number in some sense here, so negative root 1 times x. And the general solution would look like y equals c1 e to the root of -1 times x plus c2 e to the negative root of -1 times x. Now this should not be mistaken for anything immediately useful in its current form, certainly not something easily recognized. However, there is a surprising connection back to the original differential equation, and we can see that quite easily if we go back to y double prime equals -y. This is the kind of equation we looked at earlier in the course. What function is equal to, when we take its second derivative, is equal to itself but negative? If we just do a quick thought experiment, we think of things like sine and cosine being solutions to this. Well, there's a nice way to get to that in a much more constructive way, a less guess and check way, and that's by using Taylor series. If you look at this idea of e to the square root of -1 times theta, so it's just a constant times this variable. If you look at the power series or Taylor series or Maclaurin series, in this particular case it's all of these, then what you get is the function value at 0, the derivative at 0 times theta, derivative squared over 2 factorial times theta squared, and so on. That series, if you just write it out longhand and just pretend that square root of -1 means something meaningful to us, and you group the terms, you end up getting some things like the square root of -1 squared. Well, that just equals -1 if we're willing to accept that this means something. What that lets you do is group the terms together. Anything with an odd power, so theta, theta cubed, theta fifth, they all have a root -1 with them. All the even powers, though, we end up squaring away the square root, and we just get positive and negatives, and we end up with these two series down here. Those two series are incredibly famous in their own rights, and those are equivalent or exactly equal to the cosine of whatever this input is, and notice we factor out the square root of -1, so everything in here is a real number. That sum is equivalent or equal to sine of the input. All right, let that simmer for a while. It's not something that we're going to be spending a lot of time exploring this connection, but what do we have as our solution right now? We have y equals c1 e to the mysterious square root of -1 times x plus c2 e to the square root of -1 times x with a negative out front. This is what I would call true, but not useful, at least for the kinds of applications we're interested in this course. there's fascinating usefulnesses elsewhere. But for now, this doesn't make a whole lot of sense to us. However, this rule that we just explored for e to the square root of negative 1 times theta lets us translate this into a linear combination of cos and sine. Well, if we have a linear combination of cos and sine, this is a linear combination of two exponentials, it shouldn't come as a huge surprise that we could build our two solutions as, say, the cosine of x, and the second solution being sine of x, with the general solution together being y equals c1 cos of x plus c2 sine of x. Because all we're doing is exchanging the two nasty looking functions that we started with two new linearly independent functions. Cos and sine can't be added up together to cancel out, and getting a perfectly valid general solution to, let's go back for a second here, this differential equation, which was equivalent to, hey, what function's second derivative equals itself with a minus? Well, a sine or a cos. What do we find here? A sine and a cos being two perfectly valid solutions here to that differential equation, but through the mechanism of power series and careful handling of the complex number, or the imaginary number, square root of negative 1. What does this mean for us in practice? Well, if we think back to what we're going to have in every scenario with linear equations, constant coefficients, we're going to have a characteristic equation. This is going to be the r squared things. Well, if we end up with conjugate roots, complex conjugate roots, something plus or minus something times the square root of negative 1. So if we do have the square root of negative 1 in the roots to our characteristic equation, then notice the b was with the square root of negative 1. It goes inside the cos and the sine. So we're going to get two solutions. Because we have two roots, we'll get two solutions. One's going to be a cosine, one's going to be a sine. The order doesn't matter, we just usually go cosine. The other part, the a, well, this is without the square root of negative 1, or what was called the real part of the root. Well, that's what we've looked at before. If the root was 2, we would have e to the 2x. If we had 5, we'd have e to the 5x. So there we get an exponential of exactly that multiplier, e to the whatever a value is, times x. And that shows up in both cases, both terms, in our general solution. So when we get the square root of negative 1, we're always going to get these in pairs. That's a nice theorem from complex analysis. When we have real coefficients, and when we get that pair of solutions to the characteristic equation, so a pair of r values, that's going to lead to a pair of solutions to the original differential equation, e to the ax cos bx, e to the ax sine bx. We'll explore that further through a number of examples.